Welcome to the deep dive. Today, we're looking at, well, a pretty fundamental challenge facing these huge language models, the data wall. For years, we sort of relied on two things scaling up together, compute power and just sheer amounts of training data.
Right, the standard approach.
But compute keeps getting faster, exponentially even. But the supply of genuinely new, high-quality text written by humans, it's finite.
It absolutely is. And that gap is becoming a real bottleneck for how we traditionally improve LLMs.
So diminishing returns if we just keep doing the same thing.
Precisely. If you stick only to those methods, eventually you plateau because the good data runs out or becomes incredibly scarce.
Okay.
And that's where this idea comes in reinforcement learning on pre-training data, RLPT. It's pitched as a totally new way to scale, shifting focus from finding new data to getting more out of the massive amounts of pre-training text we already possess.
Right, that's a big shift. Usually when we hear reinforcement learning, like RLHF, it's something you do after the main training, right? And it needs tons of human labels, which is slow and expensive.
Exactly.
So the key thing here for you listening is RLPT gets rid of that need for human annotation completely.
Yes, it's designed as a self-supervised method. So instead of needing a person to say good answer or bad answer, RLPT figures out its own rewards automatically, just using the huge unlabeled pre-training data set.
Okay, so how does that work? Our mission today is really to unpack the mechanics behind the self-supervision and look at the performance gains they're claiming, which seem pretty significant on some tough reasoning tests.
Let's dive in.
So normally, pre-training is mostly supervised learning, just predicting the next word, basically. It's about imitation locally. But RLPT uses reinforcement learning during this phase. It pushes the model, the policy to explore, more complex paths, multi-step reasoning trajectories.
That's the core idea. To make that happen without human labels, they developed what they call a next segment reasoning objective.
Okay, segment, not just word.
Right. Think bigger chunks, phrases, sentences, maybe even a logical step in an argument. The model is rewarded for predicting a whole upcoming segment based on the context before it. And forcing it to predict at that segment level, well, that encourages it to grasp richer meaning and generate that kind of intermediate reasoning we want to see.
And the sources mentioned two specific ways they set this up, using data samples split into three parts: the preceding context, the target segment itself, and then the next segment after that.
Correct. The first task is called autoregressive segment reasoning, or ASR.
ASR sounds like standard generation.
It's pretty close conceptually, like asking the model to write the next logical sentence. It predicts the target segment, let's call it segonic, using only the context before it, $7. So yes, it aligns with standard autoregressive generation, focusing the RL on flow and coherence.
Okay, and the second one, middle segment reasoning, MSR. This sounds different.
MSR is definitely more challenging for the model. Here, it has to predict that middle segment, but it gets to see both the context before it and the segment that comes after it, ASI plus 1.
Ah, like filling in the blank in the middle of a paragraph.
Kind of, yes. You have the beginning and the end, figure out the connecting piece. It pushes the model much harder on comprehension and understanding context from both directions, a bit like masked language modeling.
And they mix these two tasks during training.
They strategically interleave ASR and MSR. The idea is to optimize both the model's ability to generate reasoned output, that's ASR, and its ability to deeply understand context, which is MSR.
Okay, but hang on. If it's all self-supervised, how do you stop the model just rewarding itself for generating stuff that looks consistent but is actually nonsense? Where does the quality control come from without a human?
That's the crucial part. The reward signal isn't arbitrary. It's based on semantic consistency. Meaning, does the segment the model predicted carry the same essential meaning as the actual segment that was in the original data?
And how is that judged?
By another tool, a separate model called a generative reward model, or you can think of GARO as an automated judge. It compares the predicted segment and the ground truth segment and scores how semantically similar they are.
So it allows for different wording as long as the core idea is the same?
Exactly. It allows for that natural linguistic variation, but checks that the underlying meaning is preserved. It's leveraging the structure and logic inherent in the original pre-training data.
So an LLM grading another LLM's work based on rules learned from the data itself. Interesting.
But there's a step before all this RL happens. They call it the cold start phase.
Right. You can't just throw RL at a base model.
No, because the RL task itself, this next segment reasoning, it requires the model to understand and follow instructions to even begin. So the base model first needs some standard supervised fine-tuning on instruction-following datasets.
Just to give it the basic capability to understand the task.
Precisely. It's like a prerequisite to even start the self-exploration process that RLPT enables.
And just quickly, what counts as a segment? Are we talking sentences, paragraphs?
Good question. The default unit they used is the sentence. They use standard tools, like the NLTK toolkit you might know, to just break the raw text into sentences. That defines your saddle hour.
Okay. Now, about refining that reward. The sources say the first attempt, a strict reward, didn't work well.
No, it was too rigid. It demanded something very close to an exact match, semantically.
So if the model produced a perfectly valid answer that was just phrased differently or maybe slightly longer?
It would often get penalized. And worse, sometimes the model would generate something sensible that actually covered multiple ground truth sentences or segments. The strict reward just couldn't handle that flexibility. Training was unstable, often just stalled.
So how did they loosen it up without losing the quality check?
They moved to what they call the relaxed prefix reward. This is the successful approach.
Prefix reward.
Yeah, basically the model gets full marks, a score of 1, if its predicted segment is a valid prefix of the actual ground truth completion.
Ah, so if the ground truth is the cat sat on the mat and went to sleep, and the model says the cat sat on the mat,
it gets the reward. Or even if it says the cat sat on the mat and began to doze, if that's consistent with the start of the ground truth.
I see. So that allows for variation and, crucially, for longer answers that might span multiple steps or sentences.
Exactly. It stabilized the training dramatically and let the model explore generating more complex, multi-sentence reasoning. That change was key.
Okay, so with the mechanism refined, let's talk results. They tested this on the Qwen3-4B base model. What did they see in terms of general performance?
The improvements were pretty consistent and quite substantial across several standard benchmarks.
Like MMLU?
Yep, on the standard MLU, they saw an absolute jump of 3.0 points. And on MMLU-Pro, which is tougher and more up-to-date, the gain was even bigger, 5.1 absolute points.
Wow. And the sources really highlight the GPQA-Diamond results.
Yes, because GPQA-Diamond is designed specifically to test deep, multi-step reasoning across lots of complex topics. STEM, humanities.
Yeah.
It's really challenging.
And the improvement there.
An 8.1 absolute point increase for the Qwen3-4B model after RLPT. That's a massive leap, and it strongly suggests RLPT is unlocking these deeper reasoning abilities by forcing the model through those intermediate steps.
Significant. Any others?
They also noted a 6.0 point gain on KOR-Bench, which covers diverse fields like law and economics, again showing breadth.
And what about math? That's always a tricky area for LLMs.
It is. They looked at math reasoning using the PASAC metric, basically measuring accuracy. On the AME24 benchmark problems, the Qwen3-4B model improved by 6.6 absolute points on pass at 1.
Pass at 1 meaning it gets the right answer on the first try.
Correct. And for AME25, another set of challenging math problems, the improvement was 5.3 absolute points on pass at 1. These are really solid gains in a difficult domain.
And it seems RLPT isn't just good on its own, it actually helps other training methods that come later.
That's another interesting finding. When they used the RLPT trained model as the starting point for another technique, RLVR reinforcement learning with verifiable rewards, they saw additional improvements on those same math benchmarks. Another 2.3 points on AME24 pass at 1 and 1.3 points on AME25 pass at 1 on top of the RLPT gains.
So the foundation lead by RLPT makes subsequent fine-tuning more effective.
It suggests the capabilities RLPT builds are robust and carry over. Yeah, it's building a better base.
Let's shift to the analysis. What about scaling? Does this method look like it will scale well as we dedicate more compute to it? That ties back to the initial data wall problem.
The scaling properties look quite promising, actually. Their analysis indicates that the performance improvements on these benchmarks seem to follow a power law relationship with the amount of training tokens used for RLPT.
Power law scaling is generally what you want to see, right? Suggests predictable gains with more resources.
Yes, it's a very favorable sign. It suggests we could potentially keep getting significant predictable gains just by investing more compute time in RLPT training, effectively squeezing more out of the data we already have.
They also did some qualitative analysis looking at how the model seems to be thinking. There's an example about solving a Fourier transform problem.
Right, and it's fascinating because it shows the model isn't just spitting out an answer, it follows a structured process.
Can you walk us through that?
Well, the description suggests the model first sort of abstracts the core problem from the context. Then it figures out the next logical step needed. After that, it formulates a possible continuation, like a hypothesis, for the next part of the solution.
And then it checks its own work.
Yes, it verifies if that step seems plausible. And importantly, if it doesn't seem right, it apparently explores alternatives. It can even backtrack and try a different path.
That sounds much more like actual problem solving, not just pattern matching.
Exactly. Generating all that intermediate reasoning content, the steps, the checks, that's what you need for complex tasks. It aligns with multi-step reasoning strategies.
So the big takeaway advantage here is that RLPT seems to enable the model to do reasoning for learning.
I think that's a good way to put it. It learns by actively exploring these reasoning paths it discovers within the pre-training data. And because it's generating and evaluating these self-explored trajectories, it seems to build stronger generalization skills compared to just imitating examples in supervised fine-tuning.
It's learning the how of constructing knowledge, not just memorizing the what.
That seems to be the goal, and the results suggest it's making progress in that direction.
Okay, so wrapping this up for you, the listener. RLPT presents itself as a really important development for tackling that data scarcity problem. It sets up this self-supervised RL objective using the ASR and MSR tasks that lets models learn more deeply from the massive unlabeled data sets we already have.
And perhaps the final thought here, connecting back to the bigger picture, RLPT is really about allocating compute differently. Instead of needing compute and endless new data, it uses compute to let the model self-explore and uncover the hidden reasoning structures within the existing data. It's trying to learn the thought process behind how that data was created in the first place.
Which could be much more efficient.
Potentially, yes. If this kind of approach lets us get significantly more reasoning power out of the data we have, does that change the equation? Does the focus shift away from the endless hunt for new data towards purely making better use of what's available through smarter algorithms like RLPT? That seems like a key question this research raises.